Okay, for case 2 for repeated real root. Example, if we have m1 is the root of the characteristic equation. If we have m k times m repeated k times, then we would be able to obtain k solution, k linearly independent solution, and that solution would be in that form. The first one is in the term of exponential of m1x. The second term is x exponential of m1x. And the third term is x to the power 2 m exponential of m1x. And the last term, just go like this until the last term is x to the power k minus 1 times exponential of m1x. So they are k terms are linearly independent to each other. So that we can write it in the term of general solution. This one for the only repeated real root. Okay, so you would get C1 exponential of m1x, C2x exponential of m1x, C3x to the power 2 m1x until ck x to the power k minus 1 times exponential of m1x. Then you got to know what is the k. Whenever we know k, then we will be able to write down the solution. For example, if we have root n like this, 3, 3, 3, 1. So that means we have repeated root of 3. How many times? 3 times. So that means our k is equal to 3. So whenever you want to write down yc for this one, for this case, using root number 1, the root m which is equal to 1 is not the same as 3. So the part of 1 is not repeated root. So when you answer this, for n equal to 1, you just use case 1 to answer that. So for this one, you get C1 times exponential of x. That's from 1. Plus, now we have 3 terms here, which is the repeated root. This one you would get C2 plus C3x plus C4x to the power 2. That's it, right? Because it said that you got to write it down until x to the power k minus 1. Now our k is equal to 3. 3 minus 1 equal to 2. So that's why it's n with this term, x to the power 2. And that's the answer. You look at only the part that is repeated, and then you use this. You use case 1. Any root which is not repeated, unrepeated, you use case 1. Any root with which are repeated real roots, you use case 2. Okay? For example, we have differential equation like this. We're saying that find the solution, find the general solution of this differential equation. Again, we got to assume y is equal to exponential of mx. Okay, and this one you repeat 3 times, right? So our characteristic equation, m to the power 3, how many m's that we can find? 3 values, okay? So we can find 3 values of m, which are m equal to -1, and then m equal to 2 and 2. So that means we have repeated roots, right? So our yc is equal to, for this one, -1, you use case 1, okay? And this 2, you use case 2 to answer, okay? So the first one, for m is equal to -1, you get c1 times exponential of -x, okay? And for 2, how many times is repeated? 2 times, right? So that means k is equal to 2. Now the way that you write down, you got, because C1 we already used it, so this one you got to start from C2. C2 plus C3x, right? Because your k is equal to 2, 2 minus 1 is equal to 1, so it's going to be n at this term, okay? C2 plus C3x exponential of 2x. Any questions? Okay. Now case 3. Complex group. For example, if we have m is equal to and it's unrepeated. For the complex groups, it always comes two together itself with the conjugate of it. Okay, so actually when you write down, you might write down this way: m12 is equal to a plus minus bi. Okay, b is an imaginary part. So actually, like the way that we write down it, we can say that y1 is equal to exponential of a plus bi x, and y2 is equal to exponential of a minus b I x. You can take it like a real root. I mean, the way that you answer, you can take it as a real root. But the thing is that you have the exponential of the imaginary part of that number. And the way that they're going to do it is that they just change the imaginary part into the side course instead. Okay? So in that case, the way that we write down is y is equal to, I put k1 first. K is arbitrary number, just like z. But at the end, I will put it into the z term. I want to put it this way first. And by that, you would get, because these two are linearly independent to each other. Okay? Okay, like this, right? Actually, the way that you plus, because you have the number which has the same base, right? It is mathematical operation. These two terms have exponential of AX the same. I just take it out. But from Euler formula, we know that e to exponential of theta I is equal to cos theta plus I sin theta. Okay, from this I'm going to change the part of the imaginary part of the complex number into the term of sine cos. Okay, so from from this definition, I can get the first term exponential of bxi is equal to cos bx plus I sin bx. K2 I would get cos minus bx plus I sin minus bx. Right? And then from the trigonometers, this is the quadrant 1 and this is the quadrant 4. When you do the quadrant 1 and 4, here is theta. If you go to quadrant 4, this is called minus theta. The side chords have the same number but different signs, depends on it's represented by x or y, right? Cos and sine, right? So when you look at the cos, you look at the x number, right? Cos theta, quadrant 1 and quadrant 4, cos theta is the same value with the same sign, plus. So that means cos minus bx is equal to cos bx. But for sine, because sine you look at the y value. Quadrant 1 you got positive x and y, but quadrant 4 you got x positive and y negative. So that makes sine minus theta is equal to minus sine theta. The same value but different sign, right? So this one you would get minus I sin bx according to this figure. Now, you have these two terms. If you look at the first term, k1 cos bx, for the second term you've got k2 cos bx. They have bx together, so you can sum them together. So you would get k1 plus k2 cos bx. The second term of k1 is k1 I sine bx, and this one is minus k2 I sine bx. We have sine bx, so we put them together. You would get k1 minus k2 I sine bx. If I have k1 plus k2 is c1, and k1 minus k2 times I is equal to c2. So we would get y is equal to exponential of ax, c1 cos bx plus c2 sin bx. So if you have the complex roots and they are unrepeated roots, then the final answer that you can write is y is equal to exponential of ax. A is the real part of the complex number times c1 cos bx. B is the imaginary part of the complex number, okay, plus c2 sin bx. So if you have the root in the terms of complex number, the final answer got to be in the sine cos term. Just use it. You don't need to derive this. I just show you how to get cos and sine. But when you do the answer of this type of root, you just use this equation right away. But you got to know that A is the real part of your complex root, and B is your imaginary part of your complex root. Okay?